All right, without further ado, we're all gathered here for this exceptional NoSQL database event tonight. We have with us a person who is the Director of Product Management for Couchbase, which basically means he's in charge of everything NoSQL at one of the leading non-relational database companies in the world. Please welcome Weigel.
Thanks, Eric. I'm glad all you guys shouted out so many features. I'm sorry for the understanding, but I hope you'll keep it exciting enough that you won't mind. Actually, we already had the show of hands, right? Who's using NoSQL? Out of those people, maybe anybody using Couchbase server today? Okay, excellent. So otherwise, you probably would know this stuff already. It's excellent. Now, what about CouchDB? There were a lot of people shouting out stuff about CouchDB. Who here knows CouchDB? Okay, so we don't need to explain a little bit more what the difference is between those things. Maybe later afterwards we can do that. Today, we really want to focus actually not less on Couchbase server and the product, even though I'm from Couchbase. It's really more about the general problem of how to go from relational system, as we say all of you guys are, to NoSQL technology, and really make you understand what are some of the challenges, how do people solve it, what are some of the areas in which it makes good sense to deploy NoSQL, and of course, there are also some areas where it doesn't really make sense to go to NoSQL. I think it's one of the standard things, right, to say up front that NoSQL for sure shouldn't be understood as, oh, it's going to replace SQL relational databases everywhere. I really think it's going to be more, it's in addition to relational databases, to solve the very specific problem that is now currently leading to data explosion everywhere. And so we expect it will be a very significant part of the database market, but at the same time there will always be some problems for which relational systems just can't be beaten, and I don't think anybody in the NoSQL space really is trying. So why are people interested in moving? So fundamentally there's been a change, and I'm sure most of you experienced that change, and that's why we're here, right? When people came up with relational databases in the 70s, the landscape was a very different one from today. Back then, many users meant a few thousands of users of the database. Actually, ticketing agents for airline reservation systems, I think, were the then heavy users of databases, right? A few thousand users today is nothing. I mean, we talked about something, I have some slides later about it. I mean, we're talking these days about millions, tens of millions of daily active users visiting a website, trying to retrieve data, and a lot more, hundreds of millions of people registering for a service and having information stored. Right? When it comes to the type of application, they used to be very formal, very rigid, right? And now you have a pace where big applications, big online sites, need to update application code on a weekly or bi-weekly basis in order to add new features and stay competitive, right? So those things have changed, and of course along with it, the technology has scaled. Memory used to be very expensive, data connections were slow, right? And now we find it terrible if you on your cell phone have to wait for like a second for a web page to load, and people complain about that, right? Things have moved on, and because things have moved on, the design decisions that were taken for relational databases don't necessarily make sense for lots of the problems that people are encountering today. And that's really where NoSQL has come from, and this is why NoSQL is really more than a fad, because it solves a problem which relational databases fundamentally can't solve. Because in order to get the functionality, to get those cool asset transactions and all those things that all of you are probably using today, you do have some requirements on the underlying system that lead to contention, that just mean you can't keep scaling out your database, you can't do flexible schemas and so on. And that really is why NoSQL is just a different area of technology for different problems. There was a survey that was done about NoSQL, and it was actually a little bit surprising. I hope all of you guys can read it. The screen's a little bit small, but the top reason why people are moving to NoSQL is actually the schema flexibility, not performance. We expected the second one, the ability to scale out, to be the #1 in these surveys for sure. But it turns out that actually one of the key drivers where people are very unsatisfied with relational systems is this fixed schema that you have in relational systems. And so let's look at that before we focus on the scaling. Those are really the data model and the scalability are going to be the kind of two key areas I'm going to focus on today. So if you look at the list of questions here, right, those are the kind of problems that I'm sure many of you are encountering when you're interested in NoSQL. Right? Do you often have lots of sparse tables? You know, it's a common problem, right? You need to add a new column to your table, but then hardly any of your records actually use it. So it's very sparse and very complicated. Then your app developers will come and keep saying, oh, they need more columns in your schema because they've got some more data they need for this latest feature that they're adding. And then, of course, scalability is the other big thing. If you often upgrade your hardware, or if you have trouble and you start to, need to do lots of caching and application level sharding, or if you start using your very expensive database as a key value store because it's the only way you can really start to shard it and use it across multiple systems, something really is wrong. So NoSQL is really where those problems can be avoided because they have the schema-less nature and most of them scale. Now, the first step actually on the way to NoSQL was probably memcached, and I'm sure what many of you have used that. It's you put a memory cache in front of your relational database in order to have as many queries or as many accesses as possible in your cache, so that you don't have to go to the database layer, and this way you take load off your database and you can live with the performance that you have. Incidentally, we actually have a bunch of the contributors to memcached that are going to Membase. Now Membase is a distributed key value store with persistence and clustering. It's kind of one of the inputs into what became Couchbase Server. Now then, this is kind of all key value based, meaning that what is being stored is a block, right? The database itself doesn't understand the data that is stored, but it can give it back at really, really high performance. Data structure service like Redis, I remember somebody was shouting that out earlier, right? It's a data structure service, it's got caching, it's got some level of persistence, they're trying some clustering, but it's really great if you have a single machine for like lists and sets, very, very convenient. Then there are graph databases, which are a little bit out there for specific problems. They are awesome, but it's really, I don't think, mainstream. They're columnar stores like Cassandra or HBase. Data model is a little bit different, but today we're going to focus on document databases, and that's where with Couchbase, I think, believe the standard is going to kind of emerge. It's where Mongo is. MongoDB is a document-oriented store. CouchDB is a document-oriented database, and now Couchbase Server as well. Couchbase Server, for those who don't know, just very briefly, is basically, so we were Membase and we merged with a company called Couch1 from Damien Katz, the inventor of CouchDB. We're currently, Couchbase Server 2.0 will combine those two. Basically, we have the distribution layer, the memcached layer for the very low latency. We've got the clustering replication all from Membase, but we're replacing the persistence layer with something based on CouchDB technology to give us incremental MapReduce distributed across the system, and cross-cluster replication, cross-data center replication, those kinds of things, kind of combining the advantages of Membase and CouchDB. And so this is Couchbase Server, which, as the distributed NoSQL document store, is kind of one of the examples we're going to look at today. So distributed document databases, what are they? I think that the biggest difference to what most of you will be used to, of course, is this document nature. Now, what this means, and we have a few more slides talking about this really, is that data isn't organized in the traditional column and rows fashion that all of you probably are used to and are using today. Instead, we say you organize data in what's called a document. Now the schema-less nature comes in because each of these documents can actually have a different structure, and the structure, the schema if you will, is actually contained within the document. And if there will be waiting outside,
there is 2 more chairs remaining over there and a few stools over here. 3 more chairs here and a few stools in the front.
3 chairs here.
Looks like over there. Is there some?
There's 3 more in the back. The last 3 chairs in the room.
Can kind of sit over there. Now, so they contain, the documents kind of contain the schema for the data that they contain. But of course, they can also be complex. They can be nested, and so you can build up very complex documents this way. Now, typically, all of these revolve around the keys. I mean, just like your regular database, you need to have a primary key. In this case, the primary key identifies uniquely a document. And so whether it's a key value store document database, if you know the ID, you can get it. It needs to be unique. The encoding formats vary. Most of them are either based around XML or JSON. MongoDB does BSON, which is basically kind of binary encoded JSON. But it's a very simple structured format. You can, for those of you who can read what's on the screen, it's like basically attributes and values. It's very straightforward, and very easy to use, and actually very human readable as well. Then, of course, for the distributed aspect, that data gets distributed, sharded across, and we'll talk about that in a little bit later. What this means is that you don't have to worry about those kinds of things anymore. This is a schema we took from some genealogy website. Now, I recently talked to somebody from SQL, and I believe they've got, is it 3,000 different tables or something in SQL? And people find it impossible these days to add to just a single column because all the table and the entire system just seems to break all kinds of code. And so, you know, this is not even a complex schema. I'm sure many of you will have ones that are more complex. And this is what all of you are used to. And there's a whole industry behind helping people to optimize those and make those good. And certainly it's very powerful, but instead of this kind of row and column and row structure, we just have individual documents that are self-sufficient and they're fully describing what's the data that's there. Now, the problem with the relational model, especially, is that typically you don't just have one table. Right? If you would have just one table, a lot of things in the relational world wouldn't be that complex. But of course, in reality, you start to have foreign keys into another table. That's the whole normalization, right, and third normalized form, and all these things where people, you know, take the data and distribute it into multiple tables and then you need to do a lot of joins across them. Great, but of course it means you need to have logging, and it's one of the key reasons why you can't shard them. It's also one of the reasons, of course, why you have these fixed schemas, because now all of your records, at least in one table, need to have the same columns, right? And so you need to do alter table if you want to change it. Instead, in the document world, it's much simpler. Well, you just write all the data that you want into a document. Just like if you have a sheet of paper and you take notes of what you want to remember in some context or something, right? You put it there and you write it in. Now the nice thing is, if you want to add something, so in this example, doing a terrible job at presenting these. At this example, it's actually meant to be an error logging use case. So let's say we've got error logs and they happen, you know, certain error happens at a certain time in a certain data center. In the relational world, you would have a table with the data centers, with the phone numbers and the locations and whatever other info. And then you have your actual error log, where you would point to which of the data center the errors occurred at. Not even very complex, very straightforward. Now, in the relational world, in the document-oriented world, you simply put all of this into one document. So you've got your error, when it happened, which data center, and the number for the data center. At this point, you might say, fine, so what's the big deal? Well, the big deal comes if you now suddenly have more information. Let's say maybe some of your components give you a component level resolution of the error, what caused the error, or a severity. Now, the nice thing is that you can simply add this into a document without making any changes to your app code. If a document doesn't have these fields because a certain error might not require them, for example, the database doesn't mind. You can mix these all in the same database, and even for indexing and querying, you can still index all of these, for example, on the data center field and look up by data center, even if some of them have other information that other records do not contain. So this whole problem of sparse tables goes away because you just add the information only to the records that actually need them, and you group them together in the logical way how you want to access them. Now, of course, the document design now does mean it's a little bit of a change in the mindset, right? So the way you design your schema is different from how you should design your document model. And so some of the rough guidance we always give is, what do you think of as a logical grouping? Like I said earlier with the sheet of paper, what would you if you describe the problem or the data to somebody, how would you logically put it together if you were writing it on a piece of paper, right? On a piece of paper, you wouldn't need a relational model. You wouldn't want to keep going through lots and lots of stacks. You would put everything together. So putting together data that's commonly accessed together, so that you access, that you need when you access one part, you typically need the other part. There is an atomicity element in here, in the sense that NoSQL databases are atomic at the document level. So meaning you can read and update and delete a document that is atomic. You don't have cross-document transactions. And that is true for basically all NoSQL databases. So as a result, if you need atomicity, you need to basically do it on a per document level. There are some ways where you can do basically two-phase commits from your application layer. There are some ways to get transactions across multiple documents, but most commonly you simply put all the things that you want in a document together, and this way you can update them atomically as the one document. And then, so this was kind of talking about the types of data, what you want to access together. Then, of course, you can also separate certain information out into separate documents and reference them. This is kind of then at one point, if you have all information you always access together in one document, and you have some of it repeated across documents, you have a lot of unnecessary repetitions, so then sometimes splitting up and splitting out certain parts of the information makes a lot of sense. And so now you simply put a reference to the other document inside your original document. Now this transaction support does put some constraints on that, but it is still very, very commonly used. Now, I think we've got an example here. So, but actually, before we go to the example, let's quickly talk about the unique key or the document ID. It's like a primary key, it needs to be unique. So that's got the same. So the typical ways of choosing one, like UUIDs, or however you generate those unique keys today works well. Now, one thing that is more common, though, is that often you end up using certain common prefixes. So, especially when you start splitting information across multiple documents, you often will have a common root. So, for example, you have your user ID, colon, and then player data, colon, level, or, And so now, once you know the ID of the player, you automatically know a certain document name, certain document IDs that will exist. Because whenever you create a new player, for example, you will create certain, 3 or 4 documents where the key is based on the unique ID of that player. And so this way, you can split up the keys, but you don't need to keep track of what the different keys are called, because once you know the common root, you can already know what the other documents are called. Plus it allows you now to access, for example, all the documents belonging to a certain player or all documents of a certain type. So as the example, we've taken a blog. It's something that lends itself, right? So you've got user information, but then you also got blog posts themselves, and you've got comments. And that's kind of the blog post and comment is always a good way of explaining different data models. So what we've got here is the first option, which is you put everything you want in a single document. It means that you have your unique key. In this case, I guess they chose the title of the blog. Fine. Then you've got the author. Actually, here you see in the title, they prefix the actual title of the blog with the author. So that's kind of something that's sometimes useful for some searches because you can now do a search on the primary key to find all the posts from the author, for example. They've got author field, the type, it's a blog post, the title, the format, the body, HTML, and so on. And then in this case, they put the comments simply as an array of comments inside the one document. So this is a very simple way of modeling it as a single document. It's great if you don't have a lot of comments in your blogs, right? This is very nice. You access the one record, and you've got everything you need to display the blog and the comments on your web page, for example. Right? You will only need to update the record when a new comment is added. It's very simple, and the simplicity makes it easy and nice. Now, if you have more complex websites, and you might want to have more and more comments, storing all comments in full inside the original document might not be the best choice, right? So at this point, you can also do what we described with the splitting part, where you now take some of the information, put it in a separate document, simply put the reference to the ID in the original one. So here now we've got the comments. It's still an array, it's still a list, but in this case, the list does not contain the entire comment. It just contains a reference to separate comment objects. Now, if you just do it like this, it's actually maybe not that exciting, but you can see how you can expand the scheme now to go to full threaded comments if you want to. So if you now have a list inside your blog entry that shows you basically all the top-level comments, and then the top-level comment has a list that points to the replies, and all the replies themselves are separate objects, you can now see how you can have, the usual thing where you show like the top-level answers or top-level comments to your blog, and then if people click on the expand this comment thread, they see the other responses, and you can very efficiently get just the entries that you need. Now this is distributed in all very low latency. The whole low latency aspect we haven't really talked about, we'll talk a little bit later about, but in general for NoSQL system, just doing lots of lookups by primary key is what you want to do, because that's where these things are extremely fast. I mean, we're talking well sub-milliseconds. If you're in a data center, I know benchmarks where in 10 GB you're talking about less than 50 microseconds to access like 2K documents or something. I mean, document accesses are very, very fast and efficient, so rather than reading one giant document, reading lots of documents as you need them and display them very fast is often the way to go. And so this is, I think, hopefully a good example of showing how splitting up these documents and then referencing them from within allows you to kind of get a little bit of the best of both worlds. You don't have one giant document, but you still have documents that are somewhat nicely to the scalability, because now that we're talking about more and more complex systems, typically you run into the problem that your relational database has difficulty scaling. And who here is running a sharded MySQL or Oracle setup? So, the other people they are not sharding the database layer at this moment at all? Okay, I'm surprised. But you that all are probably in this state right now. What this means is this is the typical kind of web architecture, right? 3D architecture. You've got your presentation layer up top, which is the browsers. We all know that scaling the web tier is very straightforward. You've got a load balancer, you've got a bunch of app servers or web servers. No magic here. Now, right now, what happens is these all come back to the one relational database that is storing the data essential for the website. The problem here is, of course, that you can only make this one database bigger. It sounds like most of you haven't had the fun experience of trying to shard relational databases. So in this case, right, you pay more and more money, get a bigger and bigger box. Maybe put a memcache layer in front of it, and trying to find ways how you can optimize your queries and all these things. But the problem is, of course, your web tier, the application servers and the web servers will scale out horizontally very nicely. You just add more if you have twice as many users. But the database, you can make this bigger and bigger, but at one point you have the biggest machine, and you just can't go bigger, then you need to start sharding. Now, even if you start sharding with relational, even if you have an Oracle rack set up which does the sharding for you, because they have a shared backend in the end with lots of locking, you still will get diminishing returns, and at one point you just can't scale anymore. And you pay all the money that's over that. And so NoSQL really goes the other way and says, well, you can scale the web server by simply adding twice as many web servers if you want to be able to serve twice as many hits. Why can't we do the same with the data layer? And that's really what it is all about. It's saying we have a shared nothing architecture where the data is truly independent, just like your app servers, right? You can add twice as many app servers to double the number of hits you can serve, because each of them is independent. They have state, but the state is local to that web server. So now you just add twice as many, the balancer will distribute it across it, it's all fine. Now, the same here is now true for the database tier, where you've got your data equally distributed across a bunch of servers, and each of them can operate independently of the others, each of them can serve data independently of the others, meaning that there is no contention as you access them, so that now twice as many database servers literally means you can serve twice as many requests. And the nice thing is, these can now be fairly simple servers. Some of you might know Couchbase. One of our first customers in Couchbase was Zynga, where membase is used for a lot of their games. And it's that scalability that made it exciting. A lot of our customers are on EC2. Some of you have used EC2 and EBS volumes. It's not exactly a data powerhouse, but the nice thing is you just have a few of those things, and in aggregate you're very well able to use that as the data tier. And the nice thing is, because they're also fault tolerant, if you have things like EBS outages or your nodes just drop because they're now not these super expensive high quality nodes, these systems can cope with it. All of them have like some failover mechanism, high availability to make sure that individual node failures don't disrupt your application. It goes all the way to, for example, Couchbase server, you can even do upgrades to the system whilst it is running. You can upgrade the software version, you can change topology, add remove nodes, all of these things whilst your node is running without any downtime. So how does it work? Well, let's first look at a single data access, and this is now, I guess I should say, specific how we do in Couchbase server. So Mongo will do things a little bit different. Most of this applies similarly to others as well, but this is now specific to how we do clustering, how we do data operations. So let's first look at a single, just document write. Now, in order to be fast, you need to be asynchronous, right? If you it's kind of one of the typical trade-offs that I'll talk about in a second. So the write comes from the application server to the Couchbase server node. As soon as it hits memory, it gets acknowledged back. Now, a Couchbase server's consistency model is strongly consistent, meaning that for each key, and we'll talk about the sharding in a second, there's only one place where a specific key will be read or written, which means, unlike Dynamo style systems that we talked earlier, for example, you're always going to get read or write, basically. And so as soon as it's in memory, any subsequent reads will get the last write. And so it gets acknowledged as soon as it hits memory. Now, of course, durability is something that people typically want from a database. And so, in addition to keeping it in memory, it also gets replicated out to other nodes in the cluster. You can select how many replicas you have. And that happens directly from memory, so it is very fast. Now then it also gets asynchronously persisted to disk to give the ultimate durability on disk. Now in Couchbase Server, by default everything is asynchronous as we show you here. If you have specific activities or specific writes for which you need more durability guarantees, there's something called observe, where you can basically at the application level say, okay, I want to now wait until, and then you've got separate points you can wait for. You can say, I want to wait until it is replicated, or I want to wait until it has hit disk. So this way you can choose your durability. Of course, it comes in a performance penalty, right? If you want to wait for the disk write, well, it's going to take a while. Like I said, this write to memory and the return, we're talking about less than a millisecond. Physical spinning disks just can't be that fast, right? Maybe worth mentioning, one interesting thing here is in the Couchbase Server case, so this is now where CouchDB is, or something based on CouchDB. It's really, we've rewritten a bunch in C, and it's really not all that much like CouchDB on the implementation side anymore. But a nice thing here is that between this memory caching layer that gives you the high performance and the disk store, there is an actively managed write queue, which allows us, amongst other things, to do data DB. A common pattern for online things is that the same document will be modified in rapid succession, right? Because the app server is doing something, somebody, a user is doing some activity, which often will lead to a lot of updates to the same documents. Disk is slow, spinning disks are extremely slow, and so by deduping it, and basically if you have 10 successive updates to a document, we write the current document at the time of writing, which might mean that we write only the last version of the document to physical disk. Which means that now we've taken the data volume that you need to write to disk down by 80% or something, depending on how your access patterns are. And so that's very powerful, especially for some of our larger properties. So this is how a single write happens. However, of course, we talk about sharding. And so with sharding, the other question is, well, how do I find out where my data lives? Right? Because you don't typically want to go through a single routing tier. You want to have the application service access directly the server that has the data so that you can get full concurrency here. And so, in our case, the client libraries, so that's the SDKs that you can download from the website, they actually have the cluster map they get from the cluster. Then there is sharding. We talked about auto-sharding as one of the features early on. What this means is, in the way we do, in Couchbase we do sharding, is we basically have a fixed number of shards or partitions. And so a specific key will be always hashed to the same partition, or we call it a V bucket or shard. Now, what changes is the mapping of these shards to a physical server. So if you have only one server, all your shards live on one server. If you've got two servers, then the documents are evenly spread out across the two, or in this case across the three. And when you say documents here, it really means partitions of the data, each of them containing a range of the key space, or rather a set of the key space. Because we use sharding, we use hashing to do the shard, the mapping to the shard, it means that actually there aren't any hotspots in your setup, because they are not range-based. So mathematically, any document is equally likely to end up on any of these servers, and so therefore your read and your write load will be evenly spread. Now we have, in our architecture, we don't have master-slave. Instead, each server has some active data and some replica data. So the data that's active, let's say, on server 1, or all the partitions that are active on server 1, are now replicated to other servers, but not just to one other server, they're split up. So you'll see that we've got 5, 2, and 9 as the partitions here. You see that, for example, 2 lives on server 2, whilst 5 and 9 lives on server 3. And in bigger clusters, of course, it's even more finely spread. Now, this means that, we'll see this later in the failover case, that now when these replicas need to be activated, instead of failing over and having one server bear the entire load that was caused by one server being down, the additional load is being spread out over a maximal setup server. And for your durability, of course, it really helps because now your replication is spread out across more and more servers, so that even in many, many node failure cases, you end up gracefully degrading with your data being unavailable rather than having large chunks being out. So now, from the application side, they can calculate which of the nodes to access to get the key they want to. They simply go there directly and they do reads or writes directly at the server. And this is how the load is equally balanced across all the machines in your cluster. Let's look at growing the cluster. This is, of course, one of the key reasons why you would want to go to NoSQL. We already said, right now you might have a workload that requires 2 servers. Down the road, you might require 10 servers. And so being able to add them once the workload is running is really very useful because capacity planning is hard, especially if it's something online where often you don't know what the update will be ultimately, right? So how we do it is, we start off, so in a Couchbase server case, you can add an arbitrary number of servers because there is no master-slave relationship, right? If you have master-slave and you want to add servers, you need to at least add, one master and one slave. If there are multiple replicas, you need to add it in that number of units. In the Mongo case, with replica sets, you need to add at least an additional replica or one replica set and so on. So there are these constraints. In our case, because we do this, each node being both active as well as replica, you can add an arbitrary number in one go. You'll simply spread both the active as well as the replica data evenly across those new machines. So this is a very cool animation, at least I still think it is. You see here, let me just do it again. So you can see how now a portion of the data on each server is being moved to the new servers, both of the active as well as the replica. And so as this moves, we see that the end state is that both active and replicas are very equally balanced across the new cluster. And so at the end of it, of course, the cluster map gets updated, and now your read and write workload is spread out across the full set of new machines. And so this is very powerful, and this is how people like ONG Pop, which I'll talk about in a second, are able to grow and accommodate very, very large workloads. Now what happens if a node fails? This high availability is, the more machines you have in your database, the more you need to worry about it. So let's say this server goes down, is unavailable. It means that now auto failover kicks in. So at this point, requests to this service, of course, don't get answered. Requests to the other servers do get still the responses like before. The nice thing is, because there are no, it's on one point of read and write. At this point, you don't have that sometimes this gets announced and sometimes it won't. Auto failover kicks in, and what happens here is, what happens after the auto failover is that the replica data for partitions that were active on the node that is failing over will now be promoted to be active. So you see how this one, for example, this partition has now become active on the server. And you saw how the replicas, by being spread out, how it becomes active across a range of servers. So there's no one machine that bears the additional load. Instead, it's a bunch of servers that each get a little bit of incremental load. And then, of course, the cluster map is updated so that now you access the documents directly from the correct server. So this was kind of a 5-minute rundown of how sharding works and how this enables you to keep your load distributed across these machines. Now, why this matters, and we already talked about ONG Pop a little bit, I'm sure many of you will know it. It was actually quite funny. We published an article about how to prepare your game for massive growth, because Zynga is one of our biggest customers, and so there's a lot of usage in the social gaming space, so we're very commonly used there. We wrote some nice articles about it, and then I think on the 7th of February or something, ONG Pop came up with Draw Something. Now, who here has played Draw Something? did that in Europe. It's very embarrassing because nobody knows it, but here some people know it. It was, of course, the #1 growing mobile app, or the fastest growing mobile app ever, or something in the App Store. What it is, for those who don't know, it's basically a Pictionary, but you have a Scrabble element where you see a certain set of letters that help you guess what your friend is drawing. It's kind of a turn-based game. You play with people you know or random people. Now, it's a great example of how these things go. So, OnJPop has been around for quite a long time, actually. They're older than Zing as a company. They had a lot of social games. They were doing okay, not great. And so they launched this other game in early February. And for a while, did their regular thing and started to ramp up. And they had a small number of Couchbase server they were using. Before, by the way, they were one of these companies that were on the MySQL PHP architecture. They found that from scaling. So for this game, lucky for them, they decided to try out the whole NoSQL thing, and so they went to Couchbase server. Now in this case, what's interesting is, it did the thing that everybody who ever wrote any app on the App Store is always screaming of. It went viral, and it went so with a vengeance. It ended up being mentioned by some guys from Jersey Shore, and apparently that has appealed to some people, and so there were more and more people picking it up, and then Miley Cyrus blogged about it, and it exploded. And what you're seeing here is the daily active users. This is how social games are typically looked at. And you see it went from a few 100,000 daily active users to well over 50 million daily active users. Now, most of these, or many of these users come back, but also the total number of registered users, of course, is much, much higher. I think it's within around 100 million or something like that. Because, of course, that's the nature of these kind of apps, is that many people will pick it up, play twice, and then never come back. But, of course, they still generate data and need to store. Now, the exciting thing here really is that within, if you look at the time frame, you're talking weeks. Like on the 1st of March, they started to be at like around 1 million daily active users, and like 3 weeks later, there were 15 million daily active users, and the bought by Zynga for $200 million. Not bad for a few weeks' work, right? But the crazy thing here is that, of course, underlying a database that needed to scale from a few thousand operations per second to tens and hundreds of thousands of operations a second, because you have these large amounts of users who all want their data access, and of course it's a game, so you don't really want to wait. And this really is, I think, showing what the power of NoSQL is. It's the ability to just keep scaling up your database tier and say, awesome, you've got more users, let's just add more servers. Because if you start your game with this amount of servers to serve that workload, that's a real.
Do you know how many documents do they have and how many servers do they have?
I do know, but we are not allowed to tell you. It's the problem with most of the same with Zynga and other companies. Players who are very successful in the social gaming space often tend to not want to share the details of their architecture or how the game's built or what their, how many servers they use and all these other things. So I'm afraid but it's a lot. You can imagine that if you play the game right, it's like per game there's some documents, then there's per user documents, there are lots of gameplays per user, so you can see how this thing very quickly explodes. Yeah. And this, in parallel to this, maybe worth mentioning, right, there was in the App Store a game, the Simpsons game, actually, funny enough, by Electronic Arts, came out at about the same time, also started off really promising, and I think a week later they had to shut it down because basically users were complaining that the game was getting too slow, and that was based on the traditional architecture where they simply couldn't cope with the growth of the data and end up scaling this with low latency enough. So in their case, for real, it meant that the game wasn't successful. And I think this is a pattern, not to this extreme we see all the time, but this is just one of these changes that I was talking earlier on this first slide about how the environment today is so different from the 70s when relational databases were invented, right? Because back then you couldn't ever have something where you suddenly would have millions and millions of additional users on a database. It just, how would it happen? They physically couldn't access it, right? only with the internet and with applications moving to the internet. And now the cost of, or the effort to start using a new app or discarding an old app and moving to a different app or picking up a new one has become so low that once, especially these ones that are free of charge or very low cost, the hurdle to enter and become a user is so low that if there's something good out there, people will just go and do it. And if you don't have the ability to scale and deliver to that demands, the users I think will just go and do something else instead. Okay, so before we move to that, I've got a final case study where we talk about tribal crossing. Yes?
So since the last one, that's sort of your poster child, it's a great success story as well as technical story. Have you tried to look at like where would this have failed? You said this is like one of the first ones they put on a NoSQL architecture.
Yes.
Have you tried to look at kind of like where it would have failed on a sort of more traditional architecture?
It's really hard to predict because, of course, if you have the traditional, like let's say you have a sharded MySQL setup, right? You can, Facebook is running sharded MySQL, right? It's not like you can't accommodate large amounts of data on a sharded relational architecture. Now it gets very tricky. Facebook has magicians that carefully scrub every line of code and take great care of their system. But it can be done. The thing is, it can't accommodate the rate of growth. Because in order to add more new servers to sharded MySQL setup or sharded relational setup in general, right, you have difficulties transferring the data. You don't have this online kind of rebalance where you can simply add nodes and keep the load running and it starts migrating to some of the new servers. Those things all don't exist. So more than the absolute capacity of the data, it's much more about the growth that you can't accommodate easily with the relational systems. Now, in addition, of course, the complexity now, if you start to move to something like sharded MySQL, you end up basically using MySQL like a key value store. That's the most common pattern that people do. And you're actually surprised when you talk to a bunch of people in the high growth areas like social gaming or ad serving and other things, where often they're just using a relational database as a key value store. They have a table with two columns. Basically, they've got a key and they've got a value in there. Because that's, once you start to shard, you lose joins and all the other fancy abilities that the database gives you. So therefore, you need to come down to the most basic common denominator, which ends up being, well, okay, I've got an ID for my data, and I've got the data itself, and everything else is happening at the application level. And that's the other reason, I think, why these sharded MySQL or relational setups really aren't such a great solution. It's because they end up not really giving you the advantages of the relational database anymore, but they give you all the pain of the relational database because you do still have the schema issues and you still are fundamentally disk-based and slow, and you need to put a caching tier which you need to manage separately and so on. Okay, and we'll do Q&A at the end, right? So before we go to the case study, maybe some other consideration that are less fundamental but very much more tactical and matter when it comes to actually choosing which NoSQL database to use. There is NoSQL for NoSQL. So implicit, but in this case it's more about when it comes to accessing your data, there isn't a standard language or format yet. There might be one, I wouldn't be surprised down the road, but right now you typically rely on the database-specific SDK to access your data. And look at what languages are supported by your database and make sure that, of course, that matches whatever language your developers are developing in or choose to develop in the future. Consistency models, we briefly talked about it. The key thing, I think, is can you live without multi-document transactions? As we said earlier, don't think of it in the context of your current way of dividing up the data. Think of it in the context of how you would model your data in a document store. Because clearly right now you will need multiple tables you need to access at the same time. But now, as you move to document model, you will put this data in one document, you still need multi-document transactions. The consistency level, talked a little bit about the Couchbase server case. It's very consistent, meaning you read your own writes. Something like Dynamo, when you have poor reads or writes, you end up potentially getting back multiple answers, and at the application level, you have to decide which one is the right one. Availability, of course, comes to what we talked about with the replication. So how is the database coping with node failure, and how can it recover? The behaviors differ between them, and it's definitely worth looking at to make sure it matches your use case. Now that is the second more boring part of operations. It always is very boring for developers, but then of course once you have the system running, it's really what's between you and the system being down typically. So making sure that there is good monitoring available, that you can do the backup and restores, upgrades and maintenance, support available, all these things that for relational systems that are typically closed source, other than MySQL, is not an issue. On the NoSQL market, where all solutions pretty much are open source, including Couchbase server, there it does differ a lot. Monitoring, for example, is wiring between the different solutions and their capabilities and their levels. Scalability, talked about this. How easy is it? Again, it varies greatly between the different offerings. We talked a little bit about how we do it in Couchbase server. Other databases make it harder to various degrees to do that. And then, of course, on the indexing querying side, the thing here is that NoSQL doesn't offer joins. It's pretty much simple as this. The reason why you can't do server-side joins is because server-side joins fundamentally require you to basically lock data and access data across multiple nodes in a cluster, which means you now have points of locking that will slow you down, where, of course, in a distributed system with various failure cases, you need to have timeouts in there, all things that don't really lead to high performance and the perfect scalability we're looking for. So what you can do is you can do client-side joins. So if it's small amounts of data, you basically look up multiple documents yourself, or you do multiple queries to get certain sets, and then you do a join in your application. That's very commonly done if the data sets that you get back from the query are small. You get like 10 or 100 responses because it's something that's maybe per user specific or something. So you're not getting giant amounts of data back. And then doing the join at the application level actually works extremely well, especially because, of course, the application is also scaled out. If you remember the slide with the app servers, you don't just have your application running on one server, you already have your applications also scaled out. So it means that the joining at the app level also is happening in parallel at that tier. Okay, so let's put it all together and talk about trial crossing. It was one of the early examples of moving from SQL to NoSQL, and so they were kind enough of giving us actually a bit of insight. So these were slides that originally represented by Triangle Crossing the authors of the game, and so there's a little bit of code inside to give you really a feel of how some of the social game stuff is done. So in this case, the Triangle Crossing game, now it's Fable Labs, it's on EC2. See, part Pokemon, part Frontier Zone, part Mario Galaxy. So you get to discover animals across the galaxy and race them in your magical garden, which is, I'm sure, all you all have dreamt of. Now, they were on MySQL, sharded MySQL before, and of course, actually they were on single MySQL servers for the game. So before, games had a single MySQL server with a Memcache delay in front of them. But the problem that they had were the things that maybe some of you are dealing with. In order to optimize it, they ended up doing a lot of explain queries to understand, okay, how can we optimize our indexes? How can we speed this up? They started to do denormalization, the thing that you always learn at first. You shouldn't do in your database, but then you end up doing it anyway because it gives you better performance. They started doing, as I said, caching of data with Memcache. They played around with the configuration of MySQL. They started to have discrete slaves or replications so that at least they could start to scale up reads. All the fun games that I'm sure lots of you, if you're using MySQL, have done or similar steps with Oracle. It's just what people do right now when it comes to scaling your relational system. Now they realized that it just didn't seem very optimal for them, and they realized that as demand grows, isn't there an easier way? They read about Zynga and other people that are leading that space doing it differently, and so they went looking. Now, their profile was they had a lot of writes because the game state gets updated on the server, so it actually ends up being much more write heavy than traditional Memcached workloads will be very read heavy, right? You've got your website and people just access something and it's mainly reads and very few writes and updates. But in social games, it's actually very common to have reasonably write heavy workloads because, well, the player does something and they want to update the state. And increasingly, not just in games, but all kinds of websites or web offerings, right, are being interactive, and what the user does needs to be recorded. Or you want to, in the ad case, for example, of course, and you just want to gather what the user does anyway. So more and more become write heavy, which means that caching doesn't help you. Because in order to, for the consistency, right, even if you have a cache in front of your database, the writes still need to go to your database typically first before you put it in cache. Then they already had a scaled down example of this viral aspect that we saw with Draw Something. They had an app called My Polls that went from 100 to 1 million users over a weekend. Now, 1 million users isn't quite 20 million or whatever, but it's still a whole lot of users if it happens over a weekend when your DBA is at home. And then, talking about DBAs, they don't really have a DBA either. And it's again one of those beautiful things about applications on the internet is that this whole DevOps model is very common. Right? You very often have that the developers, also one of the developers is the guy who runs the application, is responsible for maintaining the service. Things like EC2 means that even as a single person, you can have data centers across the world, right, and have them available. Other people take care of it. You don't really need to do very much. It becomes simpler and simpler. And so now you want to have the same simplicity for your data tier as well. And of course, saving money. And that's where that comes in, I think, is primarily because you have the flexibility on your sizing. You don't need to try and anticipate ahead of time how big your capacity needs to be. Right? And so if you talk with successful social gaming companies or all these companies that launch a new product online, they typically have a big debate between the developers who say, well, for sure this is going to be a hit, and so we need like 500 servers to run this. And then there are the bean counters who go, well, but we really only want to have 2 because if they don't get used, then we pay all this money. And so this trade-off is very hard to solve because if you get it wrong, you have too many machines, then your user experience is great, but you pay a lot of money. If you have too few machines, your user experience quickly suffers, which nobody wants. And so it's really a difficult trade-off. But because now with NoSQL you can grow so easily the size of your cluster, you can start off with a guess, and the cost of being wrong is much smaller because you can simply change it as you're running the system. So they, I guess I should say, they tried out a few different solutions. They tried out Cassandra, Mongo, and Couchbase Server, which I think 1.7 they did. It was about 6 months, 8 months ago, I think. They tried out and they ended up choosing Couchbase Server. Now they're deploying it in EC2. Very simple. They just set up the nodes. They were not using one of the smart clients because they were using Memcached before. Specific to Couchbase Server is that it's protocol compatible with the Memcached protocol, which means that you can, if you're already using Memcached libraries for your application, it makes it very easy to migrate because you don't even need to change the libraries that your code is using to access what was previously Memcached, now with Couchbase. So they were using what we call Moxie, which is the thing that basically adds this routing of the cluster map and the sharding to look up to which node to talk to. That's contained in Moxie for existing Memcached libraries. So they were running this on their web servers and then pointing it to their cluster Because it's EC2, what's often handy, right, on EC2, if the node goes down, it will come back with a different IP. So they were actually using a DNS for some of the nodes in the cluster so that they have an easy way of changing it as the nodes fail and turn over. You can talk to any of the nodes in the cluster to get the configuration. You can give it a list of nodes so that you make sure that no node going down will mean that it can't talk to the cluster anymore to get updates from the cluster map and so on. The scaling, I don't have a demo prepared, but if you guys go and just download it from the website, I promise you can set up your own cluster in 5 minutes. It's a single package for Windows, Linux, Mac OS, whatever platform. It's a single package. You install it on 2 machines, and you tell one machine about the other one by giving it the IP and the UI, and you've got a cluster. It's simple as that. There are no special nodes. There are no zookeepers, everything else. All nodes are exactly the same from one image. Is that a question?
Yeah. Sorry, maybe I missed something, but I thought that Couchbase managed the sharding, like the map and the sharding on its own.
Yes.
So what would be the purpose of using the client-side Moxie if Couchbase does that for you anyway?
Okay, so let me go back to one of the earlier. Okay, so if you look at if you use one of the SDKs, one of the Couchbase client libraries, you see that we showed on the app server how you have the cluster map on the app server in order to directly access the right server that contains your data directly from the application server, right? Now, Memcached doesn't know about the sharding that we use, right? Memcached libraries can do hashing, but they don't understand how to look up something in the cluster map to find the right node for a specific partition. So what Moxie does is it basically takes this cluster map functionality and puts it in a proxy. It's really an Memcached protocol proxy. And it runs on the application server or the web server. And so now the Memcached library will actually access the local Moxie, which will now do a lookup to go directly to the right server. So it's really only applies if you're using one of these legacy libraries. If you're using the new SDKs, then you don't need to worry about Moxie. Now, I'll come in a second ago why in their case this actually mattered. Okay, so then they access the server, all very straightforward. Let's look a little bit at the data model. It shows all these things that we talked about earlier in how they work. So, in the case of raising your magical animals in your kingdom, in your garden, so you can have a variety of plants in your farm. You can add or remove plants, and of course you can see what a player has on their garden. This is not the entire game. There's more to that game, but this is just taking an aspect of it. So let's look at some code. So how they modeled it is basically what we have described as the way of distributing the data into multiple objects. They're having a per player object. Now they do this trick that we talked about where you use, once you have the name of the player or the UUID, you then can deduct other object names relevant to that player. So in this case, let's say they have player 1 originally, then the list of plants for this player will be in a document called player1_plant list. So this way, once they know the name of the player, they know, okay, if I access this document, I'm going to get the list of all the plants that this player has. Inside of this plant list now, we have basically a list, just similar to what we have in the blog post, right? It's just a list of IDs. And so this now points to actual plant objects. And so in this case, they did kind of a similar thing. They just have the actual number, the UID, and then they actually prefix it with plant in order to generate the key of the document that actually contains the data for this specific plant. So plant 201 is a starflower apparently. Now, the other interesting thing they do here is that they actually have a reference from the plant back to the player ID. So here this is a player ID 1, which means that player 1 is the object, is the owner of this plant object. And so that's a common pattern that you end up doing, where, so here you can deduct the name of this document simply by knowing the UID of the player. But if you now have access to the plant and you want to look up whose plant is it, rather than having to do access an index or anything, you simply have the reference back within the document itself. It's a very simple way of making this all very fast without the need to go and use any of the indexes, because of course indexes will always be slower than if you already know the ID of the document itself. So then, if you want to get all the plants belonging to a player, it's very simple. You access the Couchbase client, you get the plant list. We know it's player 1, so we know the key will be player 1 plant list. And so I generate the new, I get the plant list here, and then of course, if I want to add something, I can simply add it to the player object.
So, are all these plants standard, like the star flowers that have one standard plant to begin?
I would imagine so.
So, in that case, if you wanted to get all the players that star flowers, then you would have to do this.
Yes. So you would build
where you don't really exactly know.
So what you can do is you can build still an index, of course. You can build an index by the name of the plant, and then you can, in this case, you would probably build the index and point back to the plant object itself potentially. So then you have a list of all star flower objects, and then you can either count them, or you can go and look up within them who the player is, or you can build another index that points directly to the player.
So this would be somewhat similar to what you do in a relational world.
Yes, so you certainly can still do the secondary indexing and use it. I think this is, though, to point out, right, that if you can live without indexes, and especially what is interesting about things like social games, and I think lots of website interactions is sometimes that you have an overall data set that's very large. But if you look at the data per player or per user, it's actually fairly small. And in those cases, building an index across the entire data set for everything, if every time every query will return you like 3 or 4 hits because every user only has a tiny set of data, it actually often turns out that it's really better, and you have less load on your server because you have less indexes to maintain if you try and do some of the indexing at the app level and maintain it within the document. So you certainly can do the indexing, but this is a common pattern that we see, and that really is very successful. So this was how to get all the plans. Here's how give a player a new plant. We create the new plan, set the new plan, so this will create the plant object. We can now get the information for the specific player. We can now change for the player what plants they own. Remember, the player plant list will get the plant list for that player. That was the code example we just had. And then, of course, you simply update the player plant list with the new array of the whatever you did, modifications you did. And so you can see how it's really very straightforward, even in the object model, to use this. Some people would even argue it's actually somewhat more intuitive for most people, because I do think if you go and explain something to anybody in words, you tend to use actually a document-oriented model of how you think about your data, because that's how we typically use it. Yes, so the question is, well, what happens if something crashes, right? So this now comes to you don't have transactions or multi-document transactions. So there are various things that you can do at the app level, where you can go all the way to basically doing two-phase commits within your app. So where each of these documents basically has something where you can basically indicate, okay, I'm about to update this, and this is the previous version, and so on. And then at the app level, you can, when you access the object, go, oh, this was actually in the middle of a transaction, and you can really roll back and undo the steps. And this on the web is, if you look, you'll find plenty of examples. It's typically a little bit overkill for these kinds of things. So here, what people do is, you can either, as you load a player object, for example, it depends on where it crashed. If you never reach this point, and your application, is crashed, right? If you now access the player, because it hasn't been added to the player yet, all that happened is that you have an orphan plant object somewhere in your database that isn't pointed to from anywhere. So it becomes more of a kind of, well, you have some wasted record that isn't referenced anywhere, which you can typically live with. So this is really, in this case, actually the worst I think that can happen, because you first create the plant object without pointing to it, and by the time you point to it, that is a single document, and so the write of the plant list can either entirely succeed or not succeed at all. And so this kind of comes back to this, using the atomicity of your document updates to your advantage, of where you make sure that things like a list is in one document, so that isn't spread across multiple things. So now that update will be atomic and will be one operation, so it either fully succeeds or fully fails.
So if you were maybe to this analogous of the relational world, you could maybe have an array object and your parent object for a favorite list, and then just be an array of IDs.
Yes, so this is here what they have here. This is an array of IDs, right, which is the plant list, which in the end, if you think about it, is you're basically maintaining an index yourself within a data object. You just count here what I said. You can generate this index based on the final data if you want to, but it certainly is a sensible pattern to maintain it yourself. What we talked at all about is concurrency. Probably worth mentioning. So if you have objects that can get access to multiple threads or for multiple writers at the same time, you do, of course, because your update is always a read, then you update the document, then you write it back, right? You need to guard yourself against the race where somebody else has already read the document and is writing a change back based on the last read of the document, whilst you're now going to overwrite this change to something not based on the last write. Okay, that wasn't very clear, but let me show it to you here. The simple case is you use optimistic locking, which is CAS, is check and set. It basically means that when you do read, you get a token back from the database server that uniquely identifies this version of the document. When you do a write, you can do a CAS write where you hand us back this token that we're giving to you on the read. The write will only take place if the token that was handed to us matches the token of the current value in the database. It means that if in the time between you reading the document to make your change, somebody else came and overwrote it, now at your write time, the CAS value won't match anymore, so the write will fail, meaning that you should go back and reread the document because somebody has modified it in the meantime.
Can it do a non-conflicting merge? Like, can it do a non-conflicting merge? Like, for example, version control system?
In this case, it doesn't. On the cluster application, there is actually a little bit more logic than just it fails, but for normal writes, the reason why merging, you can't do a general merge because what happens? For most cases, you don't know what the right solution is if you have conflicting writes. And escalating to some sort of resolution function would mean you couldn't possibly do, a single server in our case can do like 100,000 reads and writes per second or something, because it works on the active working set is cached in memory. So it's extremely fast. It's really meant HD kind of latencies and throughput.
So the different versions of the same document can end up in different nodes?
There are no different versions of the document. The Couchbase server, there's only one version of the document. And so it sounds like you know CouchDB, and it depends how many people there are. We can talk about this a little bit. So the model is very different from CouchDB, or actually it's probably the only one who truly has like a revision system where all the old revisions are kept in the NoSQL space. In this case, there's only one version of the document, which is the current version. On disk, there might be older versions, but there's only one active version. Okay, so talk about the CAS. The nice thing about CAS is it's basically free if there's no contention, meaning if the token that you hand us back matches the token that we gave you on the read, if there was no overlap in operations, there's no overlap in the system. All it is, well, I guess the additional bytes transfer, but that's it. if you have high contention documents, you can actually do a get with lock, where you can truly lock the document to prevent other people from getting it. Just this is now more akin to what you get in relational databases. Of course, now it also means you solve the same problem, because if now get with lock, you have to time out what happens if you're a reader and unlocked and so on.
Which level is important? Is it record level, document level? Is it doing page logs? Is there a way to control
Document level. So,
only document level?
yes. So the index here, I guess, on the entire locking, just because in the NoSQL space sometimes locking comes out right. In Couchbase server, the only logs, so there's no per node, read write or anything like this. The only logging that's happening in Couchbase server in regular operation is for each partition, so each vbucket, of which we've got 1024 in the system, each of those ends up being represented in memory and as a hash table, and then each of those hash tables has multiple logs. And so, because this is all memory, there can never be page faults or anything like this. So, for the regular read-write operation, there is really no lock contention at all. And if you want to do the get with lock, that is locked now at the document level, but this is different from, this kind of locking doesn't happen in regular operation. This locking only happens from the user initiating, because now the lock is actually held over a meaningful period of time, while the regular locks that are being used as you read and write data to the database are held for microseconds, because they work strictly on memory for accessing a sub-portion of the hash table. Okay. Now, let's talk about the actual migration part. Sorry. One of the interesting things that they and quite a few others did is, for applications that are already using Memcached, migrating to, well, specifically Couchbase server, because it's Memcached protocol compatible, is actually fairly straightforward. What people have done is, they start running their MySQL database, which previously they had a cache in front of it. They use the same logic that they used with Memcached, now with Couchbase server. What this does is, so the way you use Memcached is typically, you do a read, you first look in the cache. If the data is in the cache, you read from the cache. If not, you go back and access it from the database directly. The same logic applies now, except for the Couchbase server, because it's a database and not a cache. It won't forget items. So once you've written to it, it will always return them and never ever forget them. So this way, you can actually gradually migrate your data from MySQL and Memcached to Couchbase server. Basically, you do the same logic that we have right now, if the data isn't in Couchbase server, you go and retrieve it from MySQL. You then write it to Couchbase server, and so the next time you're looking for the data, it will be found in Couchbase server. A nice effect of this, nice benefit of doing this as a gradual migration of existing apps, is that the data that gets migrated first to the NoSQL system ends up being the frequently accessed data, because that's the data that you were looking for right now. And it's actually a great way to slowly migrate to NoSQL in a very non-disruptive way. Some people maintain the MySQL data for a while as well, and gives them kind of a safety feeling and a warm, fuzzy feeling about using new technology. And so this is a really gradual way of starting to deploy NoSQL technology. Okay, so this is now when they ended up. They had kind of a medium-sized cluster. It was, I think, 9 nodes or something. This, by the way, is part of our the monitoring. And then this is some more detailed monitoring that we have. One interesting thing is you really see how many of these applications are cycling. So what we showed here is the operations per second. On an hourly basis or something. And you can see how they have these daily peaks, and then this was probably like a Friday or something when, over the weekend, before the weekend, the usage level went up. Now, one of the things that, when this matters is, if you remember, we were talking earlier about how in Couchbase server everything goes to memory and then asynchronously gets persisted to disk. Now, with this model, one of the nice things is it also decouples your disk storage from your application. And so if you can live with the disk write queues growing in size during the day, it means that your disk throughput only needs to be able to cope with the average throughput and not with the peak throughput. And that is actually very powerful because disk throughput is one of the most expensive things for people to provide, right? And if you have to move to SSDs and a fancy RAID system, it gets very expensive. And people do that typically because, well, for their peak needs, they need to have high throughput. In this case, you can simply use the memory node as the buffer. So during the peak times, your disks might not be able to keep up with the right throughput. But then, as you end up moving towards the low times of the day, now your disk write queues will drain, and by the start of the next day, they are all empty and ready for more action. And so that's another kind of nice property that you get by using memory to decouple your systems. It's another reason why sizing is somewhat easier, or you can end up with less hardware because you use it much more efficiently. And this actually, no, this doesn't show the disk write here. Well, the disk write queue in their case apparently was able to keep up. It just here at one point, I guess in this first spike or something, they weren't, and you see on the disk write queue ended up peaking and being non-zero for a while. And in certain some of the larger properties, you see how this pattern is exactly the pattern you see for the disk write queue, where the disk write queue kind of grows and then shrinks again down to zero during the off times. Okay, so to end finally for Travel Crossing, they found that they did save money. It made it very easy for them to manage it. They had a single tier. Performance, of course, went up. They were able to scale. One of the key things, or one of the interesting things, and this comes back to this schema flexibility. It's interesting how these performance and scalability aspects, do matter, and to some they are key, but to many other people, doing the schema and the application ease, the development ease, is so crucial, and that's actually one of the things that they told us as well. They just had more time to just develop the game, and they didn't have to worry about, doing alter tables and all the impact of deciding to add more data and change the schema, because now they were schema free and it didn't matter anymore for them. And they, so Couchbase Server 2.0 is a combined thing where you now have the indexing and querying capability, and so they don't use that. With that, I think we come to the query part, to the Q&A part. Thanks so much for staying. I was getting terribly hot.
Before we move on to Q&A, I want to give a great big thank you. And I want to give a great big thank you also to the ladders for providing this amazing space. Can I just, before we go on to Q&A, can I just do it by show of hands here? Who here's a DBA or a programmer or a developer? Okay, wow. Okay. Anyone who had their hands up and is looking for a career change, please talk with Jacqueline. Oh, Jacqueline's gone. Talk with Andrew, who's right here. They are hiring. So, okay. The way it works, we have how many more left? We have a remote control helicopter and some more shirts. So basically, whoever asks a question gets a shirt. Whoever asks a really good question gets a remote control helicopter. So, who's the first question? Holy cow, it's a lot of hands all at once. All right, next one.
I actually got several questions for Benari. When you showed the slides, and for example, when you said that when the node goes down, the data of the other nodes, the data is activated. So when the node goes back up, what happens? How do you avoid duplicate?
Okay, so the question was around if a node fails, it gets automatically failed over. What happens if the original node comes back? The nice thing is, we're using OLE broadcasting. All the nodes are talking to each other. Once a node goes down, A gets told about, and when it comes back up, after it hasn't talked to the cluster for a while, it comes up in a state where it doesn't serve any data until it has heard from the rest of the cluster what the situation is, basically, what it's responsible for. So as it comes back up, it will first not serve anything, and if contact to the cluster gets established, it gets told, you're not responsible for anything anymore. And so it will be staying dead, and you can then re-add it as a new node, and it will get new data. But you don't have to worry about some of the old data becoming resurrected.
Okay, then, sorry.
Well, we're a little short on time, so we're going to do one-on-one with the speaker afterwards for follow-up questions, if you don't mind. So I'm sorry, just we're so short on time. Yes?
With MySQL, you mentioned before with key value database, you can use MySQL as key value.
Yes.
Now with that, what kind of performance did you get? And then you also showed there's a migration path that you can use with MySQL. Would it be smart to have a separate database which is strictly key value to migrate it into a planning migration?
Okay, so the questions around is it a good approach to start using MySQL as a key value store and then migrate that to a NoSQL database down the road? For sure, it makes it very easy to migrate to a NoSQL data store. If you're already using MySQL as a key value store, the migration path is very, very straightforward because from the application logic, you don't have to change anything. Any document database can work as a key value store. Performance-wise, you're going to see huge differences. MySQL by itself, of course, is disk-based. It has a lot more logging and a lot more work to do on every transaction. For comparison, like I said, Couchbase Server, you can basically work at MySQL speed, so a single node can do hundreds of thousands of operations per second. You get sub-millisecond, even sub 100 microsecond access latency, depending on what network infrastructure you have. Something that MySQL relational databases just can't do, and it's not because we write better code, it's just we have to do less when we give you the data, and so as a result, we can do it much faster.
Yes.
Does CouchDB still also lend itself for data analytics and OLAP-style aggregation?
So questions about CouchDB, I guess that's actually, I think I have a slide in here. Because it keeps coming up. So as I said, Couchbase is the merge between Membase and Couch1, and we have Couch now a name, and sometimes people get terribly confused. And so we're not the same as CouchDB. We have the people who wrote it, and we're using some of the CouchDB technology, but there are very different beasts that solve very different problems. CouchDB is a single node database. CouchDB does not do clustering, despite the name actually standing for clustered system. CouchDB itself doesn't do clustering. CouchDB doesn't have any of the caching layer. It's simply a disk-based system. It's has very good replication capabilities, and it's got the MVCC on the display and so on. But in Couchbase Server, as you see here, once we're using the storage architecture, data synchronization, and so on, and JSON same format, and use the same way of doing views, so all your view definitions from CouchDB will work. We now add the sharding, we add the clustering, we add the replication built in, the memcached layering, and so as a result, the semantics also change. We don't have revisions per document when you write, and so there's lots of differences.
What I mean is, if you want to do like pie charts and graphing and analytics over massive data, instead of getting a plan, let's say you wanted to say what plan is the most popular.
Yes. You can. Okay. So you have the incremental MapReduce, which is a way to do the either distributed indexing or distributed full MapReduce. So now it's incremental, so unlike the Hadoop-style systems where you run every time over your entire data set, it's more like indexing where we just update, you write a data set and just get incrementally updated for the new data written, and that includes the reducers. And so you can do things like dashboards for, leaderboards are a common case, and other things of doing simple analytics in real time, and networks now distributed with Couchbase Server.
Thank you. How good of a CouchDB is in cases where the amount of data really, like vast majority of data cannot exist in operating memory. So you have, for example, like terabytes of data.
So questions about what if you have a lot more data than you have memory. Now, you said CouchDB, did you mean CouchDB or did you mean Couchbase Server? Okay, so CouchDB, I really shouldn't talk about CouchDB. We actually focus on the best people. In general, CouchDB actually does pretty good with disk-based data where it's very large, simply because CouchDB uses an on-the-speed tree, so it's as efficient as it can look something up on disk pretty much. If you have more and more data than you have memory, it means less and less of your B-tree nodes will be cached by the operating system, so you actually have disk leaks, but the way of accessing it across the disk is very efficient. In Couchbase Server, when we now isolate it with a caching layer, you can have a lot more data in a node than you have memory. The sizing in general is though you want to keep your working set in memory. So that means the data that is closely accessed to at any time, you want to size a cluster that fits in memory across your cluster. And then that's how you get the very high performance that you want. I'd like us to more questions.
In this model, we can have a different loading for different nodes. How we can manage loading between nodes?
Well, so the question is about basically the load between different nodes. The reason why the load is very much identical across all nodes, and that even applies to the very large customers with very heavy usage, is that the mapping from the keys to this V-bucket or partition is a hash, it's CRC32. Now, that means that this is entirely random from a mathematical perspective, how it's spread out. So, if a node has V-bucket 1, 2, 3, it won't have, oh, these are all the users starting with A, which will be very hot. And so, as a result, you literally find that because we have 1,024 of these V-buckets spread across your servers, that the load both for reads and writes is literally identical across the nodes in your cluster. And because each node gets served the data from memory, it also means that if the same document is hot, the only real limitation you have on a node is your networking bandwidth. Which means that if you have a hot key, it still doesn't really bother the system because it's just served from memory and just copied into network.
So whoever asks the next question better make it good because I want it to be a helicopter question. Helicopter question, let's...
I have a question.
You can't shout it out, come on.
A lot of application frameworks that are becoming popular these days, whether it be Rails and so forth, seem to have the relational structure as sort of the default. You don't have to think about the database setup with those frameworks. How difficult is it to either migrate or even just start from scratch with sort of the NoSQL?
So this is integration.
Give it to somebody else.
So there are more and more integrations happening with ORMs into the frameworks like Ruby's. Actually, for Ruby, we're just writing one. There is one available now as a mapper that makes it easier. In general, as query capabilities grow and these abstraction frameworks become more and more aware that there is a set of databases that might not have certain capabilities, it will become increasingly common. And as a user, at one point, you don't have to worry anymore. What data is stored is used underneath. You just use the model that you use for all the other apps, and it completely is abstracted. So right now, it's available for spin source as one and Ruby, but more and more on the way. And if you want to write one, by the way, just to say later, right? Remember, this is all open source. So if you have your favorite framework, you want the integration of your favorite database, just contact whoever makes the database, and in our case, just as everybody else in the NoSQL space, we'll be happy to help you guys and integrate it into your framework of choice.
Actually, we are using the DB, and I saw you mentioned you don't support HTTP API anymore. The HTTP API. So yes. What is the we use the list function? Do you support a list function?
No.
View.
Views we still support. So it's about specifically if you want to, if you're in Couchbase, you want to move to Couchbase server. As I said, they're trying to do different things. As a result, we changed APIs. For example, the HTTP REST API to access your data. It's very convenient. The problem is you can't make it very fast because you have to go to the HTTP stack on both sides. You can't ever get the sub-millisecond access latency and the high throughput that we need. So this is why we're using binary and HTTP protocols. But the view API is still the same. So your views will move as they are, just being now parallelized.
Thank you. Holy cow. Quick one. The guy next to is pointing to you, so double what we get it.
Yes, I had a very good question. You mentioned earlier about Mongo and other. How does, what's the key differentiation factor for Couch from Hadoop?
From Couchbase and Hadoop? Well, it's really, I think, for different different cases, right? Hadoop by itself is more of an analytics framework. It doesn't try to be real-time, but it's able to handle very large amounts of data for complex MapReduce jobs. Right? Couchbase Server does have the incremental MapReduce, but it's a single-step MapReduce function, so you can use it for simple analytics, but you can't do it for very complex analytics. It's really designed to give you low latency access to your data, both for reads as well as for writes. So I think it's very different. It's more the OLTP case versus Hadoop being more OLAP, I think is kind of the easiest way to think of it.
Wow. Yeah, you had a migration. Can you explain the cluster map rebuilding? So if it's built in the nodes here, then does each node rebuild the cluster map? How does that work?
Okay, so the question is about the cluster map. I was thinking that might work in high That's actually, well, it depends how much you thought about this question, but it's actually a fairly complex problem on how to agree on a cluster map in a clustered setting. The way it's done is even though all nodes are the same, at runtime a leader gets elected, the server of the state can only be modified by the leader. This way you avoid that multiple nodes trying to update a new cluster map as topology changes. If that node goes down, a different node gets elected. The clients receive the data, the cluster map from any of the nodes in the cluster. When they send a request, they actually say, I specifically want data from this partition. And if they have an old vBucket map or an old cluster map, the server will simply say, I'm not responsible for this partition anymore. So this way you don't have to worry about all your clients needing to be synchronous in updates into their cluster map. They can be arbitrarily out of sync. If they don't have the current map, they will be told they don't have the current map, and then they will go and request the latest map from the cluster. So this way, we've solved the problem of, in a distributed system, you can't really do things, you can't update all nodes at the same time, and this is how that's happening.
That was indeed helicopter worthy. Yes.
Using Solar and there's ranking keyword search, there's other results, and they support what they call a facet. So is there any something similar on that roadmap?
Okay, so questions about Solar for full text search, of course, right? The way we are solving the full text search problem is we're actually integrating with Elasticsearch. Also based on Lucene as the indexer, but instead of Solar, it uses a slightly different model on top of it. It maps well because it's station aware, and so we are having a connector that uses our cross data center replication technology to connect to an Elasticsearch cluster. And so this way, the Elasticsearch component, you can use with all the capabilities of Elasticsearch. So you can do faceted search and other things, full text indexing on that. The way we recommend to use it is, of course, that you don't keep the source document in that index or in that cluster. Instead, you simply what you store is really the reference back to the original source document, because the source document itself you want to access from the Couchbase server cluster, which is much lower latency. And this way, you keep the index size down in your full text search cluster, and then you just retrieve the full document from Couchbase server. And that's a very
you mentioned about that, we got one-on-one afterwards. I'm sorry, we're out of time. This is the last question, Jimmy. You got it.
Yeah, I have one question and one creative. I have one question. I have one question and one creative. Should I take the question or the creative?
You choose.
You got like 20 seconds.
My question is, how, in a world of cloud, how do you handle the concurrency on a different, like geolocated server?
Different geographies?
Different geolocated server. How do you handle the concurrencies?
Meaning two data centers in two different locations?
If you have the server based in different locations, how do you handle it?
Well, so if you want to have the same data set in multiple locations, so let's say you have Amazon East, West, and Europe, and Asia, whatever, that's where you use the cross-data center replication. So you have a separate cluster that contains a copy of all the data in each of the locations. Now we use cross-data center replication, which allows active master writes, and then they get replicated to the other locations, and you can build up flexible topologies.
Last question, yes.
Give me a
It's about when default?
We're running out of time, so
I
we'll
give
do
you
later
one
on
more.
afterwards. Last question?
So with mobile potentially, mobile potentially online tags, you know, you guys, there's not really much besides HTML5 original storage cross platform, and there's really nothing which allows you to say cache and then sync. Are you guys planning to develop?
Questions about mobile? We have a few open source projects right now. We've got SyncPoint server, and TouchDB. TouchDB is a very lightweight version. Basically, that has the CouchDB protocol, but it doesn't use Erlang, so it has much faster startup time. It's much lighter weight. That runs on a mobile device. It's available for iOS and Android. And then SyncPoint is managing the sync pairing and interaction to a CouchDB-based backend at the moment. And then, so that's out there right now. And we're looking at integrating with Couchbase Server to integrate with the big database. So talk to me afterwards now. You can point us and keen to hear more what you want to Couchbase.
Okay. Frank Weigel, Director of Product Management from Couchbase.